Well, if you learn what we want you to learn, you get it.
Will they go, like, on Tuesdays in discussion, will they go over, like, the quizzes? When we get
Well, it's your prerogative to ask questions about anything you wish to ask questions about. But you have to stimulate this discussion. We don't make a point of doing reviews on purpose. That's your job. But if you have questions about any stuff, you ask. That's why we have CLC in office periods. The key will be posted soon. I'll tell you when it's posted. When you get back to quiz, which you will get back no later than next Tuesday, if you have questions about any of the problems or questions on the quiz, your first job is to look at the key. Your second job is to consult your TA who graded your paper. And then if you're still perplexed or confused, see the guy at the head of this game. That's me. Don't be bashful. Don't be shy. You need assistance, and many of you will, because this stuff is tough. Go get it. Now then, I have to go to North Florida Regional tomorrow at UGG, 6:30 in the morning, for a fairly routine medical procedure. So, given that they are not going to let me loose until they're convinced I'm all right, and I come awake from the anesthesia and such as, if I get here tomorrow, it won't be till late afternoon. They told me I have to go home and rest. The hell with them. I mean it. If at all possible, I'll be here tomorrow. But I doubt that I'll make office time. So I say that in case you were to come look for me tomorrow and not be able to find me. Now, on with acid-base chemistry. We've laid foundation for appreciating the conceptual aspects. What's an acid? What's a base? What's a strong acid? What's a strong base? What's a weak acid? What's a weak base? Now let's get at the quantitative aspects of Bronsted-Lowry acid-base chemistry. And you will find out that after we get through this, it'll take a while, you will be able to take any water solution and analyze it in sufficient detail so as to be able to report the concentration or amount, if you know the solution volume, of each and every species that's in that solution whose existence depends on pH. And many species in water solution have an existence which depends on pH. This is a pretty powerful tool. We are now going to begin to assemble the consideration, examine them in detail, to the extent that you will be able to do what we just said you're going to be able to do. All right. First, we have to learn some new terms. First term to learn is Ka. Second term to learn is Kb. In our acid-base table, likely you've noticed there's a column of Ka values. That's in between the acid column and the base column on the table. By definition, Ka for chemistry and water solution is an equilibrium constant which measures the strength, the ability of a Bronsted acid to react with solvent, water. Nothing else. React with solvent water to produce hydronium and the conjugate base of the reacting acid. Same idea for defining Kb. An equilibrium constant which measures the strength, the ability of a Bronsted base to react with solvent water to produce the conjugate acid of the reacting base and hydroxide ion. Of course, the fact that this shows production of hydronium ion tells you why the reacting species is an acid. The fact that this produces hydroxide ion tells you why this species is a Bronsted base. So, the respective equilibrium constants, Ka for the hypothetical acid HX and the hypothetical base X minus, which of course is the conjugate base of HX. Here they are. So now we're to these considerations, definition of Ka and Kb, simply carrying on with the knowledge we've already developed in Chapter 17 for writing an equilibrium constant expression. Question. Look at the acid-base table. We mentioned that Bronsted-Lowry acid-base chemistry has been studied in solvents other than water. The Ka values you see in your acid-base table all reflect the ability of the acids, the corresponding acids in the acid column, to react with water, the solvent, nothing else. And as we've noted, produce hydronium ion and conjugate base of the reacting acid. If we were to do a bunch of Bronsted-Lowry acid-base chemistry investigations in solvent ammonia, how would the Ka values compare? Would the Ka values be the same, larger, or smaller than the Ka values you see in the acid-base table? Pick on acetic acid. Given that you did some work with acetic acid, already this term in 46 laboratory, acetic acid solution, and you did some work with acetic acid solutions in 45L. The Ka value you see tabulated is 1.8 times 10 to minus 5. That reflects the ability of acetic acid to react with water, to protonate water, create hydronium ion and acetate ion. If I measure the Ka value for acetic acid in ammonia solvent, will I get a bigger number, same number, or smaller number? What will I get? Well, in your mind's eye, if you consider acetic acid reacting with ammonia, for which the products are ammonium ion and acetate ion respectively, is that reaction large extent or small extent? Is it large extent or small extent? I'm asking. Look at the acid-base table. Acetic acid molecule reacts with the ammonia molecule, making ammonium ion and acetate ion respectively as the products. Is acetic acid a stronger acid or a weaker acid than ammonium ion? Stronger. Is ammonia a stronger base or a weaker base than acetate ion? Ammonia is stronger. So the extent of that reaction is large. But when acetic acid reacts with water, and you get hydronium ion and acetate ion respectively, is the extent of that reaction large or small? Small. Hey! Does that keep with a K value that's smaller than 1? Because a K value that's smaller than 1 tells you what about extent? Because now we got to provoke you to start thinking about numbers and what they mean. A K value that's smaller than 1 tells you what about reaction extent? I want a numerical response. A K value that's smaller than 1 tells you what about reaction extent? Less than how much?
100%.
Less than how much? 50%. That's right. Because a K value of 1 shows a 1-to-1 equilibrium ratio of products to reactants, doesn't it? That means the starting material is converted to an extent of 50% to give the products. So now you're starting to learn what these numbers mean. Okay? So if I have a large extent reaction, the K value is going to be bigger or smaller than 1? Bigger or smaller than 1?
Bigger.
Bigger. Bigger than 50%. That's large extent. Right? How about that? So, If Ka, acetic acid, 1.8 times 10 to minus 5, and you just recognize that acetic acid reacts with ammonia to a large extent, which is going to give a Ka value bigger than 1, you know that acetic acid is going to be a strong acid in ammonia, because it reacts with ammonia to a large extent. Enough said. Now then, let's take another look at these Ka, Kb expressions for the conjugate, Bronsted-Lowry conjugate acid-base pair HX and X minus, respectively. KBX minus. Here it is, I rewrote it. See? Now I'm going to do some real fancy arithmetic with this Kb. I'm going to multiply it by the molarity of hydronium ion, top and bottom. Does that change anything numerically? Same thing as multiplication by 1, isn't it? But what does this fancy multiplication by 1 demonstrate? It demonstrates that we now have turned Kb, in this case for X minus, into a combo of hydroxide ion, hydronium ion molarities multiplied times each other for an equilibrium system, with water being the solvent. That's Kw, isn't it? And leaves molarity of HX up top, numerator, divided by molarity X minus times molarity hydronium ion denominator. Here we have it. Does this combination of terms look like something we got up here? Does it look like the inverse of this? Doesn't it? It is the inverse of this. So it's 1 over Ka, in this case for the acid HX. So we've demonstrated Kb for X minus is equal to Kw divided by Ka for the conjugate acid of the base X minus, the base for which we considered its Kb value. So we've shown this. Kw is equal to Ka times Kb for a Bronsted-Lowry conjugate acid-base pair. That's important. Back to the acid-base table. Do you see why it is not necessary to list Kb values for the bases that are in our acid-base table? Why is it not necessary? Not necessary. Because now you know how to calculate every one of them if you want them. So I don't need to list them. You know how to get them. On the other hand, if I gave you a table that contained a bunch of Kb values with the relationship we just derived, you'd be able to calculate Ka for all the acids if you needed the Ka values. So let's apply this consideration. We've already recognized that hydrogen carbonate ion is a unique Bronsted-Lowry acid-base species because its position in the acid column in our table shows you that hydrogen carbonate ion, is a stronger Bronsted acid than water. Simultaneously, its position in the base column of our table shows you that hydrogen carbonate ion is a stronger base than water. A unique species. There are a few other such species in our table. You examine the table and you'll find them. What is Kb for hydrogen carbonate ion? How do I calculate it? Specifically, to calculate Kb for hydrogen carbonate ion, which Ka value do I need to use? A Ka value that's in our table. Tell me the number. I want to hear yops. Bingo. Because that's Ka for quote-unquote H2CO3, hydrated CO2. Is the conjugate acid of hydrogen carbonate ion, is it not? Oh, no. So we got 1.0 times 10 minus 14 divided by 4.0 times 10 minus 7. Give me the gee whiz result. I do not want to push button calculator computation. 1.0 times 10 to the minus 14 divided by 4.2 times 10 to the minus 7. Let's take 4.2 times 10 to the minus 7 and gee whiz it as 4 times 10 to the minus 7. (1.0 times 10 to the minus 14 divided by 4 times 10 times 10 to the minus 7. What do you get?
It's like 1 over 4.2 times 10.
What do you get? 2.5 times 10 to the minus 8. Bingo. So we now know that the true value for Kb hydrogen carbonate ion is a little bit smaller than 2.5 times 10 to the minus 8. A little bit smaller. Because to do this arithmetic, gee whiz, 4.2 is 4. Well, 4.2 is a little bit bigger than 4. So to do the computation, we're really dividing Kw by a number that's a little bit larger than our gee whiz 4 value. Now if you use your push button calculator, you'll get 2.4 times 10 to the minus 8. That's Kb to 2 sig figs for hydrogen carbonate ion. Okay? Now then, if I gave you a value, pardon me, a table of Kb values, not Ka values. Kb for which base would you use if you needed to calculate Ka for hydrogen carbonate ion? Kb for which base would you use to calculate Ka for hydrogen carbonate ion? What is it? Carbonate ion. Bingo. Just want to make sure you know how to use this relationship. That's all. Now then, let's take you to the home front. Home front being the place where you probably have some hydrogen carbonate ion. Just a second. Let me see if I can find some quick and fast. Number 4. God damn, this is whatever. So. Got any of this stuff at home? For baking, cleaning, and deodorizing. Good toothpaste. A little bit abrasive, but good. Grind that junk right off your teeth. Deodorizing. The makers of this pure baking soda, Arm & Hammer. Suggest that if you have foul odors in your refrigerator, get a box of this, tear the top off so you expose a fair quantity of surface area, and put it in the refrigerator, and it'll soak up the bad odors. I, however, suggest strongly that you remove from the refrigerator the stuff that's causing the bad odors. I think that's much more sane and direct in dealing with the problem than using a bunch of boxes of baking soda to continue to soak up the bad odors. Because as long as this rotting stuff is in there, the bad odors are going to continue to develop. We're going to take this home, or at home, take some of this and dissolve some of it in deionized water. Question: is this water solution of sodium hydrogen carbonate acidic, basic, or neutral? And if it's acidic, is it strongly acidic or mildly acidic? If it's basic, is it strongly basic or mildly basic? Now you got 5 choices. Strongly mild acidic, strongly or mildly acidic, neutral, strongly or mildly basic. That's 5 choices. How many of these choices do you think is right? Just one. If you're going to play this game by guessing by gosh, you got a 1 in 5 shot of guessing the right answer. That's not very good odds. I guarantee if you try to get through this course by guessing right answers, you may as well pack your bags right now and go. But I'm going to be a believer that you're all here with the true desire to learn. Ha! So the hell with this guess and gosh stuff. If you want to play games like that, go to Las Vegas. Good luck. What's the answer? First, acidic, basic, or neutral? Well, let's have a vote. If you don't vote, maybe I'll ask for the Tennessee tickets. When every guy on your team is better than every guy on the other team and you lose. Something not going right in the thinking department. But we'll let that pass. I guarantee the Gators will learn a lot from what happened to them on Saturday. Really, you learn a hell of a lot more from a loss than you do from a victory. All the time. You want to get good? You play the good people, the strong people, the people who likely beat the living hell out of you. Then you'll learn. But some people thrive on simple victories where they keep beating up on people who can't compete. I have no use for such people. None. There's no gain from such an activity as that. Unless you'd like to see another entry in the win column. All right? Ka for hydrogen carbonate ion. It's in the acid-base table. What do you see? And Kb for hydrogen carbonate ion we just computed, didn't we? 2.4 times 10 to minus 8. So now let these numbers talk to you. Does hydrogen carbonate ion on reaction with water react more effectively to make hydronium ion, or does it react more effectively to make hydroxide ion? Hydroxide ion, because Kb is how many times bigger than Ka for hydrogen carbonate ion? How many times bigger? How many times bigger? I still haven't heard the right answer. 2.4 times 10 to the minus 8 divided by 4.8 times 10 to the minus 11 is not a tough problem. What's the result? No pocket calculators. Answer's 500. You can do this. Provided you make yourself do it. Because I know what the hell's been going on in high schools and grade schools the last many years. Arithmetic is no longer being taught. Arithmetic is no longer being learned. Many times in the past many years, students are in my office for assistance, and what do they stumble on? Arithmetic, not chemistry. 10 to the minus 2 times 10 to the minus 1. And they reach for the calculator. I'm already in a rage. That's the way I do it. Not anymore, damn it. What's the matter with you? Use the best calculator you got. This thing. And if you need to dust off the cobwebs, then do it. I assure you, if I come across any grade school or high school arithmetic math teacher who has students use calculators to solve a problem the likes of which I just described, I will horsewhip that person in public. And then I will tell them, you do it again and I'm going to hang you. That's it. Because you're wrecking America, damn it. And I don't like that. I object. 30, 40 years ago, America was #1 on an international ranking basis for educational quality and standards at the university level. Number one, last I looked a few weeks ago, we're 28. It's because of junk like this. People who don't know how to teach are teaching. What the hell good is this? And who pays the bill? You pay the bill. It's not your fault. If you're not good at doing arithmetic, it's not your fault. But I know damn well, simply because you were able to get into this class, you have the ability to do it. So I appeal to you, do it. Knock off those cobwebs. Let that push-button device stand until you absolutely need it. I mean it. Our language is two parts, folks. Numbers and letters. Alphanumeric. And if you can't speak and understand and communicate successfully with the numeric part of our language in science class, you are lost. I don't want you to be lost. I want you to succeed. America depends on you. And these crumbheads who are not preparing you properly, I have no use for them, no patience with them at all. They got to be gotten rid of. And I mean every word of that. All right, on we go. Now then, what do the magnitude of these K values mean? We recognize that our bicarb solution is going to be basic because its Kb value is larger than its Ka value. Will this solution be mildly basic or strongly basic? What do you think is the significance from an extent standpoint of Kb bicarb 2.4 times 10 to minus 8? Remember we just talked a moment ago? A reaction that goes 50% has got an equilibrium constant value of how much? 1. This Kb value is on the order of 10 to minus 8. Woohoo! You think that's going very far? And then, after it goes to this very tiny extent, equilibrium is achieved. So will you find bicarb solution to be strongly basic or mildly basic? Yeah, good. On we go. Another so-called mystery which textbooks have a habit of stumbling on all over the place, all the time. Not always. Some get it. Do not believe that Ka water and Kw water are the same thing. They are not. You know the value for Kw, 1.0 times 10 to minus 14. And in our acid-base table, you see the value for Ka water tabulated. Why the difference? Let us revisit this reaction with which you are quite familiar. A reaction that we know. For water solution, if we take the hydronium ion molarity and multiply it times the hydroxide ion molarity, provided we're doing this at normal lab conditions, we'll get 1.0 times 10 to minus 14. That's Kw. The molar ion product for the ions derived from solvent. Kw. Well, what's Ka water? Now we got to let these Ka-Kb expressions talk to us again, since we've already had them talk to us earlier. Ka water. Does this reaction show acid water reacting with solvent water to make hydronium ion and the conjugate base of the reacting acid? So, by definition, this reaction not only corresponds to Kw, it also corresponds to Ka for water, and it also corresponds to Kb for water. So why is it that Ka water and Kw water are not the same value? There's hydronium ion times the conjugate base of solvent water and acid water. But one of these represents solvent, because we've already told ourselves that in water, Ka reflects the ability of the reacting acid to protonate what? Water, period. That's solvent water. But the other one of these is reactant acid water. I don't care which one I identify as such, because I can't distinguish between. So when I want Ka water, I got to put the molarity of reacting acid water in the denominator. You remember the molarity of water? Liquid, in pure water liquid? 55.3 moles per liter. So Ka water follows from Kw divided by 55.3. And that's where we get the value 1.8 times 10 to the minus 16. Which, of course, as we've already reminded ourselves, equals Kb water. All right? So how about Ka hydronium ion? You see that in the acid-base table too, don't you? You think Kb hydronium ion Ka hydronium ion and Kb hydroxide ion, you think the numerical values for these Ks are identical? They are. Let's pursue this one with this relationship. Keeping in mind that this expression holds for a Bronsted-Lowry conjugate acid-base pair. Okay? Kw, 1.0 times 10 to the minus 14. What is the conjugate base of hydronium ion? Water. And what's Kb water? 1.8 times 10 to the minus 16. So Ka for hydronium ion is Kw divided by 1.8 times 10 to the minus 16. 55.3. All right? Now how about hydroxide ion? What's conjugate acid of hydroxide ion? Water. How about that? And Ka water is 55.3. Pardon me, 1.8 times 10 to the minus 16. So, if this is now corresponding to Kb hydroxide ion, I take Kw, which is 1.0 times 10 to the minus 14, and I divide it by Ka for the conjugate acid of hydroxide ion, which is water, and for which the value is 1.8 times 10 to the minus 16. So what do I get? 55.3. That's it. All done. And you can write out the reaction equations if you want to do it that way. Same thing. No difference. Now we proceed to a consideration, at least on an introductory basis, which you will see we will use quite regularly throughout Chapter 18 and then again in Chapter 19. And in subsequent chapters as necessary. Called material balance. First, let's write this. I could write a number of examples to illustrate the material balance concept. Based on the chemistry shown by this equilibrium reaction. An equilibrium reaction which reflects what happens when you make a water solution of acetic acid. Coupled with this statement. Here's the statement. It's in the notes, so you don't have to try to hurry up and write it down. From a Bronsted-Lowry acid-base standpoint, see, I wrote that up there. From BLAB standpoint, from Bronsted-Lowry acid-base standpoint, the material forms of a species are those which are produced in water solution by H plus gain or loss. I should have said viable material forms. What's the word viable mean? Viable. What's that mean? Possible forms. Forms that can in fact exist. Based on this chemistry then, what are the viable material forms for acetic acid?
Acetic acid.
Well, acetic acid itself, and what else? The viable material forms from a Bronsted-Lowry acid-base standpoint, which means producible by H plus gain or loss. Does this reaction not reflect the ability of HAC to lose H plus? So the viable material forms of acetic acid are acetic acid and acetate ion. Done. Now, if acetic acid in water solution had a measurable ability to collect H plus and make H2AC plus, I'd have to tell you. Be no other way for you to know. That's a non-existent species to my knowledge for acetic acid in water solution. So for acetic acid, from a Bronsted-Lowry acid-base standpoint, the viable material forms are acetic acid and acetate ion. Now how about water? MbH2O equals sum of moles H2O itself have we recognized that water in water solution demonstrates an ability by reaction to capture H plus and become hydronium ion? So that's a material form of water. Have we recognized that in water solution, water has the ability to react and lose H plus and become hydroxide ion? Bingo. Now then, is it imaginable that hydronium ion can still collect H plus and convert to H4O2 plus? Well, if we want to know something about the ability of a species to be a possible H plus grabber, what should we do? What? Fluid structure! There's a little structure for hydronium ion. Plus charge is really on the oxygen. Does this still have a non-bonding pair? Available for potential bond formation with another H plus? You're damn right. What do you think the likelihood is of this ion reacting with a second H plus and becoming this? We recognize it's possible, it's got a non-bonding pair. But keep in mind, This thing already has a plus charge on oxygen. You think it's easy to add another plus charge to an atom which already has a plus charge? Is that easy, Coulomb? No. It's not easy, is it? Because pluses repel each other, don't they? Upshot. Even though we recognize this to be theoretically possible, because of the structure of hydronium ion doesn't react with H plus and form this. If it did, we'd have to tell you. Then I'd have to give you the experimental results which would back up the existence of such a species. All right, let's go to hydroxide ion. Can hydroxide ion lose H plus? Of course. And if hydroxide ion loses H plus, to what does it convert? Oxide ion. O with a charge of 2 minus, or minus 2, I don't care how you write it, okay? Is oxide ion a viable material form of water in water solution? Yes or no? No. Look at the acid-base table. What do you know about the base strength of oxide ion? It's stronger even than hydroxide ion. Upshot, if you put any source of oxide ion in water solution, oxide ion will react with water to what extent? 100%, and become what? Hydroxide ion. So that's it. Those are all the possible material forms for water in water solution from an acid-base standpoint. In a moment we'll show you why this is important. Now then, let's go to the next page, page 1822. Now I'm going to tell you to do something. Page 1822, as it presently stands, has got some goofs in it. So regarding the information that I'm trying to get across from page 1822, I want you to pay attention to what we have to say. Okay? Consider 1.0 liters of 1.0 molar 8Z hypothetical acid, in which 8Z ionizes 95%. Is that a large extent? You're daggone right it is. Here comes the question. Is HZ a strong Bl acid? If HZ was a real species and we wanted to put HZ in our acid-base table, here's hydronium ion. Here's water. Acids are getting stronger bottom to top. Bases are getting stronger top to bottom. From this information, can we decide where HZ goes in our table? Does it go up here? Stronger than hydronium ion? Does it go down here? Weaker than hydronium ion? Or is it possible that HZ and hydronium ion have the same strength? And if HZ and hydronium ion have the same strength, what measured property of HZ and hydronium ion would be common to each? What measured property would be the same for each? Ka, right? We already recognized Ka hydronium ion is 55.3, didn't we? So here's my directive. Starting Friday, from this information, because you now know how to do this, from this information, I expect you to calculate Ka for HZ. And in so doing, you will answer the question. And then after we calculate Ka for HZ, we'll do a material balance analysis of this solution to see if it follows with the strength assessment that we've made for HZ. Pick it up from that point next time.